So, welcome everyone to the Green Power Future Mission National Pilot Webinar Series. This is the fifth in the series, and today we'll be hearing from UK-based colleagues speaking about some projects from the Longer Duration Energy Storage Innovation Programme in the Department for Energy Security and Net Zero. And I'm delighted to be joined today by some of our partners from Cheesecake Energy and SynchroStor, and they will be introducing themselves in due time. But first of all, for anyone who may be unfamiliar with Mission Innovation and the Green Power Future mission, I'll go through some slides on that now. So Mission Innovation was launched at COP21 in 2015 and is the main intergovernmental platform for accelerating clean energy innovation involving 23 countries and the EU represented by the European Commission, as well as numerous collaborating organizations. And these members are responsible for greater than 95% of public clean energy research, development, and demonstration investments globally. Mission Innovation is structured around 7 missions, which are public-private innovation alliances that are setting goals that will lead to tipping points in the cost and scale of clean energy solutions. And those 7 missions are shown here on the slide. But of course, we are the Green Power Future mission, so I'll focus more on that. So the GPFM's goal is to demonstrate that by 2030, power systems in different geographies and climates are able to effectively integrate up to 100% VRE, variable renewable energy, in their generation mix, while maintaining a cost-efficient, secure, and resilient system. And we do this through knowledge and capacity building, demonstrating innovative solutions, and generating the tools, data, and networks needed to enable more regions to be powered by affordable VRE. Like all of the other missions, the GPFM is a public-private partnership made up of in-kind contributions from its member countries and organizations. Italy, China, and the UK are the co-lead countries, and you can see on the screen here the many other members that we have in our coalition from around the world. The GPFM splits its work across 3 main pillars. The first is led by China and focuses on the generation of VRE from the likes of wind and solar power. The second pillar is led by Italy, and it focuses on the grid, system flexibility, and market design and regulation. And the third and final pillar is led by the UK and focuses on data and the digitalization of the electricity system. And now I'll talk quickly about the GPFM's first flagship project, which is the 5 Demos in 5 Continents project. So the goal of this project is to establish 5 large-scale demonstrations of innovation activities in the 5 continents of Asia, Australia, Europe, and North and South America, which can demonstrate up to 80% VRE integration by this year, 2024. These demonstrations are made up of 80 national pilots on the scale of millions of euros and are aimed at reaching technology readiness level 6 to 7. And each of these national pilots is tackling one or more of the 50 most urgent innovation priorities identified by the mission. And you can find out more detail about all of those pilot projects in the National Pilots Report published on the GPFM section of the Mission Innovation website, where you will also find more of our core documents such as the action plans and annual reports. And then just before we get started today, I wanted to show you the webinar schedule as it stands. So you'll find the links to the previous 4 recordings on the GPFM website, or you can also find it through our LinkedIn. Today we of course have the UK, and then in December we have our GPFM conference in China, so there will be no webinar that month. And then of course January is a very quiet month, so we'll be starting again in February with Icebreaker 1, and then beyond that we're still looking for volunteers in the new year. So on to today's agenda. We've set up this webinar series to facilitate the sharing of knowledge and lessons learned in order to accelerate innovation around the world. These webinars are relaxed exchanges where a few project leads will give short presentations before we open the floor to the audience for some fruitful discussions. So please feel free to submit your questions in the chat at any time throughout the various talks, and we'll get to all of them at the end. And with that, I will be handing over to Danielle from DESNES to give us an overview, first of all, of the Longer Duration Energy Storage Program. So Daniel, over to you.
Thank you very much, Craig. I'll be talking about the Energy Storage Innovation Program. I'll be focusing on the longer duration energy storage program within our energy storage innovation. So I'll start off by giving an introduction of our net zero innovation portfolio. I'll move on to talk about the storage aspect, the storage at scale and longer duration energy storage programs. And then I will give a brief overview of some of the projects that are building demonstrators of innovative technologies. So our net zero innovation portfolio is a portfolio that's aimed to support innovation that would lead us to net zero. Within that, we have different programs focusing on different areas such as greenhouse gas removal, advanced nuclear, and disruptive technologies, etc. Within that, we also have the longer duration energy storage program and the flexibility innovation program. And these two programs were selected as national pilots for the GPFM's 5 Demos in 5 Continents flagship project. And it's the longer duration energy storage program, which we'll be focusing on today. So in our energy storage program, or generally, we had storage at scale and longer duration energy storage demonstration programs. The storage at scale program was aimed at higher power and energy rated projects, and the longer duration energy storage demonstration program was aimed at helping to develop innovative technologies. Within that program, we had two streams. Stream one was focused on technologies who are a bit more mature at a higher TRL, and they would be funded with the condition of having to secure additional private investment. Stream two were fully funded projects at a lower TRL with the intention to help them develop their technology further and improve their TRL level and hopefully avoid the valley of death. In that program, the projects would make prototypes in an operational environment and use those demonstrators to show that the technology is working in relevant environments. The funding for these programs in the beginning was around 67 million, and after some reallocations, the program for Stream 2, which looked at supporting innovative technologies, the funding for that was increased to 55 million. These are some pictures for reference. So on the left, there is that Highview project, which recently secured funding. So it's a very large system. And on the right, there's a picture for scale of Infinity, which would also be very large in its footprint and its energy and power ratings. In terms of timeline, we started with phase one, which was the feasibility study with different projects. We had 19 projects given a funding of £150,000 each to show how they propose to build a demonstrator and do deeper research. Then we selected some of the projects through a competitive down selection to build an actual prototype of the technology. And in that down selection, we ended up selecting 7 projects with the aim of helping them move from TRL 4 or 5 to TRL 6 or 7. The objectives of our programs were as follows. We wanted to help explore ways for cost reductions for long duration energy storage technologies. And in order to do that, we wanted to give an opportunity to innovative technologies who might be seen risky because of their early stage, but in the process of exploring cost reductions, we wanted to de-risk that initial step where non-conventional technologies would be able to show how they perform, and that demonstration would then secure buy-in from commercial investors in the future for larger scale deployment. We also wanted to demonstrate the capability of these technologies, and in the process of developing so many of them, we would learn a lot about how they perform in the real world and different constraints they might have, or other information that would then inform policy development for the longer term. And through that, we hope to build a pipeline of storage technologies in the UK for both domestic use and also to explore export opportunities. In that stream too, where we had projects at DRLs 4 or 5 who were aiming to build demonstrators, we had 3 categories. We had an electrical category where projects would take electricity from the grid, store it, and then give it back to the grid as electricity. We had the thermal category where the electricity would be stored as heat and then used for heating purposes. And the power to X category where electricity would be used to store as a different medium. It could have been anything, hydrogen or ammonia, etc. Within that, we have one hydrogen project. So we'll have an opportunity to listen from Cheesecake and SynchroStor later on, as Craig mentioned earlier. Now I'll move on to give an overview of the other projects we have in our stream too. We have StorTerra, who are building a flow battery based on lithium and sulfur. And the idea is to use lower cost and sustainable materials to build a system that is more safe and secure and long lasting than lithium ion batteries, while using the modularity of their cells, which use a cylindrical formation. The second project we had was Re-Energize, who are a high-density hydro project. The fluid that they use is 2.5 times more dense than water, which means that the height differential used for deployment of that system is 2.5 times smaller than pumped hydro projects, which means that more sites are potential candidates for the deployment of the system. SynchroStor and Cheesecake will present their technologies later on, so I will leave it up to them. Yeah. We also have Sunamp, who are using a phase change material to build a heat battery for thermal storage purposes. And in that project, they would be, in addition to developing their battery technology, they would be trialing it in houses within the UK, gathering their data through the winter months of how the technology performs and how the user's feedback is. And based on that, we'll have different learnings in terms of the use of this technology to reduce carbon-based heating methods. University of Sheffield is doing another project in which they will use 2 technologies, phase change materials and thermochemical storage, in order to trial heating in homes. There are homes and in the University of Nottingham's Creative Energy Homes campus that are used as a living test site. So the technologies worked on and developed by the project would be trialed here. And lastly, we have the depleted uranium hydrogen storage project, which will be looking into using depleted uranium, which is a waste product from nuclear reactors and other nuclear activities. And the aim would be to use the fact that it is very good at storing hydrogen at high densities, and to use it as a metal hydride hydrogen storage mechanism. Its demonstrator would be installed at the UKAEA site at Cullen, and in partnership with Urenco and the University of Bristol, they would look at developing not only the design, but also the supply chain of depleted uranium. So that concludes an overview of the LODES program. And I will now pass on to Mike from Cheesecake, who will discuss Cheesecake in more detail. Thanks.
Perfect. Thank you very much, Danielle. And hello, everyone. So my name is Mike Simpson. I'm the Chief Commercial and Product Officer for Cheesecake Energy. We're delivering a low-cost form of compressed air energy storage. Before I get stuck in, just a big thanks to give to the Department for Energy Security Net Zero. Obviously, you just heard about the LODES program. It's been absolutely transformational for us. Really an exciting opportunity that we've really got stuck into. Really enjoyed it, and it's really moved us along in terms of our technology maturity, in terms of our customer traction, and in terms of our ability to engage with investors. So yeah, big thanks to DESNZ for kind of setting up that program. A lot of work went into setting it up and to continuing it. So yeah, fantastic to be able to participate. Very grateful. Okay, so on with our technology. So the problem that we set out to solve was really around three things for our commercial and industrial customers primarily. Now, they're facing a pretty tough trio at the moment. A lot of them are facing high energy costs. The UK has pretty high energy costs, but they're not alone. There's obviously the pressure to decarbonize. I think there's even more incentive for us all to up our game on that with recent developments, and challenges around grid connections. So it can be a long wait for new infrastructure, particularly if it involves transmission upgrades, and that is getting in the way. So we need to be able to address that and help customers to solve their problems without necessarily waiting for the grid to solve them for them. Now, of course, there are lots of existing energy storage solutions, but some of them have some drawbacks for the kind of markets that we're looking at. So lithium-ion is fantastic technology, but it does have a limited lifetime. It does tend to degrade over time, especially if you're using it hard and using it with deep discharge cycles. And there are fire risk considerations, which hopefully we'll see big improvements in, but it does reduce the ability to use it in some contexts. Technologies like flow batteries are again really exciting, and we've seen kind of some nice breakthroughs in those technologies as well. But some of them are still reliant on pretty toxic or hard to get hold of elements, and they take specialist skills to maintain. Now, the critical mineral dependency of both lithium-ion and some flow battery technologies is something that we're going to see, I think, more and more of in terms of volatility in both price and availability. So when we're talking about critical infrastructure, that's a sensitivity that not everyone can tolerate. And then finally, and this is something that I think that Jacob of SynchroStor and I feel passionately about, inertia is something that we've had for kind of many years from our fossil-fired power stations, and we're taking those off the grid. The ability to use energy storage to put some of that inertia back on the grid with the help of spinning electrical machines, synchronous machines, that's something that is really useful, and it helps us to be robust against changes in frequency, helps to give us more time to respond if a kind of a power plant goes offline. So that's something that our technologies can deliver that existing kind of battery type technologies don't tend to. So we're looking at how we can use our system with local renewables to be able to solve really tough problems for industry, for businesses and industry. And the way we go about that is using existing technology. So we've taken proven engine-based technology, we use it in a way that doesn't produce any emissions, but that's the foundation of our system. So we put our own proprietary intellectual property together with this trusted hardware to to deliver a really sustainable and kind of low cost form of energy storage using compressed air. And that's all about helping our customers to move faster in their transition plans, help them to access the lowest cost energy and cut down their emissions. Lots to play for. So this is our system. So we're storing electricity in the form of heat and compressed air. The reason we do that is it allows us to tap into existing supply chains that are available at a volume, allows us to use existing materials, and it's hardware that will last. So we're looking at a 25-year plus service life for our systems. That all adds up to a really competitive offering in the market. It's also a tough system. So we care about resilience and being able to kind of resist kind of shocks. It's something that is able to be maintained locally. It's tolerant to different high temperatures. Some of our kind of customers are in the mining space where kind of 40, 45, 50 degrees C is not uncommon. And of course, we have that real inertia as well that gives it stability. And then finally, sustainability is something that's always been a core part of what we do. So this is a system that is made of readily available materials. It's easy to recycle, mostly steel. And we use a circular economy approach. We reuse a lot of existing kit. I'll talk more about that shortly. All of that adds up to a kind of system that has a low carbon footprint because we can reuse the hardware that is already available. And that comes together into a modular design for a system that delivers 200 kilowatts up to a megawatt hour. And we can scale that 200 kilowatts and a megawatt hour. We can scale it up to 50 megawatts and up to a gigawatt hour of capacity. We tend to focus in the kind of 5 to 20 hours capacity range. So we can cycle more or less every day is where we tend to operate. So in terms of how the system works, we take electricity from renewables or from the grid, use that to drive an electric motor that turns an air compressor. It's a piston air compressor. As the air is compressed, it heats up, and we capture the heat in our heat store, and we capture the air in our air store. When we want to get the electricity back, we run the process in reverse. So we take that pressurized air, we heat it up, and we put it back into those same piston machines, use it to drive the piston and turn the motor as a generator. So we're producing electricity once more. And that could be supplying electricity to industry, to local microgrid, to electric vehicle charging, whatever's required. Now, I mentioned reusing kit. So when it comes to those piston compressors that I just mentioned, well, those started off their life as truck engines. And we're not burning any diesel in them anymore, but we're using the pistons to compress the air. And obviously they're capable of handling much higher temperatures than any normal compressor. We use pressure vessels repurposed from the compressed natural gas industry. So these are steel pressure vessels, readily available, produced in large volumes. And we also use sand or gravel for our thermal store. In terms of some of the advantages that this gives us, we are able to draw on existing workforces as well. So we're able to use existing supply chains. Kind of, in terms of people who know how to maintain a diesel engine, there's plenty of those around, and people who are able to design, service, kind of deliver parts for these units. That's really helpful to be able to tap into. It's all about being able to work with partners. As a small company, that's a valuable thing for us to do in order to be able to get to market quicker. Actually being able to tap into existing manufacturing capability, that speeds us up. It means we're not having to build factories or gigafactories to be able to solve these problems. And those engines, again, they unlock a lot for us. So we're using older generation of truck engines, which allows us to kind of reuse what would otherwise be a waste stream and turn it into something valuable. And we put our own proprietary technology on the top of those engines. We replace the cylinder head with our own hardware, and that's what allows them to run as both compressors and also expanders. we have a focus on commercial industrial applications across the mining sector, off-grid industry, and islands, and kind of looking at business parks and mixed-use developers as well, where it tends to be driven by grid connections on the mining side, and the off-grid side, it's more about how can you deliver power at low cost, where it would otherwise be pretty tough to get kind of reliable power. You might be relying on a lot of diesel in the alternative case. And then we're also looking at how we can kind of sit alongside utility scale solar and helping to deliver kind of the small to medium scale solar parks, help them to move forwards and help decarbonize our energy system. So this is a kind of view of our prototype system, showing some of the key parts. And we've deliberately spaced the system out so that we can get access to all the different internals. It's designed, it will ultimately be a kind of fully containerized package, but being able to access different parts as a prototype has been really valuable, and be able to kind of make changes, make upgrades as we learn more about the system and as we develop. So that's certainly one of the lessons that we've valued from this project. We have our air store. So that's the kind of the slightly rocket-looking tower on the left. So that's a big pressure vessel that was fabricated locally. We have our thermal store, which in this case uses sand, and that's 3 levels of thermal store, because we have 3 stages of compression, so there's 1 per stage. And then we have the engines or the compressors, expanders inside an acoustic enclosure, and that's where they operate and deliver the compressed air and heat from. We've also got control and power cabins on site, as well as a welfare cabin for our team. One thing that we have learned from this project is that there was a lot of cabling, a lot of signals to manage. The way we'll do things going forwards is rely much more on remote input-output kind of approaches, so remote I/O. So that's something that we'll be able to simplify. It will speed up our commissioning, speed up our installation. So looking forward to kind of introducing that. Okay, so moving on to kind of lessons learned. One of our key lessons has been around our team. Now, our team is our biggest asset. It's kind of what makes everything actually happen. But I will say that development programs are demanding. They're tough. They're tough on kind of human resources. And what that means is actually the more time we can spend with our team in close proximity, physically together, and actually spending time on site where the testing is happening, that's shown kind of real advantages for kind of team cohesion in terms of team kind of strength, and be able to resolve problems really quickly. So even having an office just 5 minutes down the road, it's not the same as having people physically co-located, solving problems together and getting through the challenges to really speed up the development. Another angle to that is we recently hired an in-house recruiter, and that's been a big step forward for us as well. So we have been able to speed up the flow of candidates, of really good candidates, into our business. That's been a huge asset for us, and has been a marked improvement versus external recruiters. On the supply chain side, we've actually learned a lot about working in a kind of relationship-based model with kind of partnering with our supply chain, and that's shown really good results in terms of getting much faster turnaround times, getting through problems much quicker, and being able to be in the same room. So having one of our suppliers, for example, seconded their chief design engineer for us for 2 weeks, and working closely with him, able to really get through a lot of work very quickly. So that's been really powerful. And then on the circular economy side, so I've talked about some of the advantages it brings, and it unlocks existing supply chains, existing servicing capability. It also brings some wrinkles, having to do some of the legwork with the big original equipment manufacturers. Even getting hold of part numbers can be a challenge. So just something to be aware of. There's lots of advantages, but some costs as well. So this is our system. This is it in the flesh. If you're interested in coming for a visit, do let me know. My email will be on the next slide. This is our thermal compressed air energy storage system. I'm really excited to be bringing this to market, and again, fantastic support from DESNZ to help us do that. It's a low-cost, sustainable, and very flexible system. Hope you've enjoyed, and thank you very much for listening. And if you want to hear more and potentially even get involved, do get in touch. Thank you very much.
Yes, thanks for that, Mike. I think we'll just jump straight to the next talk, and then we'll get to all the questions at the end. So over to Jacob from SynchroStor.
Thank you, Craig. I will bring up my presentation. So, yeah, thank you, Mike, for sharing the update on your project, and thank you, Danielle and Craig, for the opportunity to speak today. My name is Jacob. I'm CEO at SynchroStor. We're an innovator in the pumped thermal energy storage space. I'll give you an overview of our project technology and the LODES project. And like Mike did, I think now's the time when we're substantially through the project to take advantage of a bit of feedback and look at lessons learned, which hopefully will be of value to everybody on the call. So who are SynchroStor? We call ourselves a startup, but the company was founded 7 years ago by Professor Wyn Rampen. He's chair of energy storage at Edinburgh University. The project began as a small project within the university, but I'm happy to say that we're fully spun out and on our own facilities just south of Edinburgh in Scotland. We've got a big team now, 25 people, and we're quite proud of the know-how we've got in the team. It's not just about demonstrating that the technology works, but it's all about understanding the journey through the MRL as well, the manufacturing readiness level. How do you make something production ready so that when the time comes to enter the market, you can accelerate that entry phase and get the product into the market a little bit faster than you would do otherwise. And of course, we've been beneficiaries of the LODES program, both phase 1 and phase 2, and I'll talk about the value of that phasing a little bit later. So why are we all doing this? Why are we pursuing energy storage, and why do we need longer duration energy storage? This is a cover page from The Economist a couple of months ago. Solar is very much a topic that's a global talking point, but to deploy more solar, we need energy storage, and I'll explain why. If you look at how solar generates during the day, you'll typically see a curve like this with peak output at 12 noon, but nothing at night, of course, and a gentle ramp up in the morning and a ramp down in the evening. Now, if we look at the UK grid and how solar has contributed to the grid over the last 5 years, we see a trend like this, steady growth. But with that comes a corollary problem, because the price that you're capturing at midday is decreasing because everybody's exporting that solar power at the same time, and they can't control the time that they export that. So the duck curve, which I'm sure you're all familiar with, looked like this in 2019, but we've seen a gradual evolution of that too over the years. And as you can see, the peaks are getting higher, the troughs are getting lower, and the spread between the peaks is getting broader. So what this means is that the challenges facing a solar developer for a future project are quite extreme. They can invest in the solar panels, which are extremely cost effective, but they see a price capture that's not looking too attractive. So what can they add to a project to improve the ROI on a project? And the answer to that is, of course, energy storage. So the solar developer can go to market now and they can buy lithium-ion batteries for a very reasonable price from various suppliers around the world. Those are typically aimed at project sizes of 1, 2, 3, maybe 4 hours duration. But to really maximize the value from the solar farm, they might want more hours than that. And that's where lithium-ion batteries tend to get a little bit expensive. They're not always the right product for static applications. So that's where solutions like ours and Mike's come into play. The question then you ask yourself is, well, what duration is actually needed? And then you need to take a slightly broader view and not just look at individual projects, but how the overall grid is evolving. We've worked very closely with LCP Delta. They're a UK consultancy who have a very powerful UK network model. And they've looked out to the 2030, 2035 period. And by their estimations, they're going to be in an annual period, there'll be up to 100 instances of either lack of power or overpower from renewable sources requiring storage of between 15 and 24 hours. And the sweet spot seems to be between 15 and 16 hours. But if you had an asset with sufficiently low capex that you could deploy storage of up to 24 hours, you could take part in almost 95% of the events on the grid over an annual period and attract the very largest revenues. So if you combine that capability with capability to load shift export from a renewable installation you might have, then the value add of energy storage becomes really quite attractive. So that's the backdrop. That's the market that's there, and it's calling out for storage. So what's our solution? Our solution is what's called, like I said, pumped thermal energy storage, and we're using a closed loop Brayton cycle. So the Brayton cycle in itself is not new, but we're bringing some advantages to the system, some key innovations. We've got a schematic here. Hopefully you can see my cursor. If we follow the flow of energy around the system during a typical charge cycle, we have a motor generator running a compressor. This takes 20 bar gas and compresses it to 200 bar in a single lift. And that also, not only does the pressure increase, but the temperature increases too. That flow of gas we feed through a heat exchanger, and it feeds a flow of solid material, which goes from ambient temperature up to high temperature, typically about 400 degrees in our installation. After that point in the cycle, the gas has lost its heat energy, but it still has pressure energy. We can extract that through an expansion cycle, also part of our unique compressor expander, returning some energy to the grid. At that point, the gas then becomes very, very cold. So we can do a similar heat exchange process and take that cold and use that to cool down some material to a very low temperature, about 140 degrees minus C. And then the gas continues round in the closed loop and starts again. So you may run this for a charge cycle. It could be, depending on the end user, let's say 6 hours. And after that 6-hour charge cycle, we'll have a thermal store of very hot material and a thermal store of very cold material. That can be held in storage for a number of hours or even a couple of days, depending on what the use case is. And then the whole system can be run in reverse using the same powertrain and the same equipment, all runs in reverse with some losses, of course, to export energy back to the grid. So the unique selling points here are bespoke equipment to result in low losses and a very careful choice of materials and material handling to keep the capex extremely low. So what does this look like in practice? Here's a render of what a commercial plant might look like. It's extremely compact. We estimate that the power density is such that we're about we require about half the land area of an equivalent lithium-ion plant. And using construction techniques that hopefully look familiar to anybody with industrial background, we're looking at something akin to car parks or sheds, and all the power equipment containerized, much like Mike at Cheesecake has chosen. Containers are a very cost-effective way of modularizing things, with the key premise that you can build things off-site in a factory, bring them on-site, and do final assembly and commissioning on-site with the minimum amount of time and cost associated. So in terms of selling points, we've got a list on the left here, appealing to ESG targets, safety and footprint, and also being able to offer the ability to load shift and inertia, frequency control. But ultimately, it all comes down to cost. And this is what we hear from stakeholder after stakeholder. And the comparison point is always against lithium-ion, just because that's the go-to at the moment. It may not be who we're competing with in the longer run, but it's a necessary step to make that comparison. So conveniently, a consultancy called Modo Energy, very well respected, used some data from NREL and BNEF to produce some data just 2 weeks ago. So on this graph here, we've got the solid line, which is future costs of lithium-ion batteries, and the dotted line is cost today. So we can see on the left-hand side of the graph, for short durations, battery costs are low, like I said earlier, and that's of huge benefit to those who want short duration storage. But if you want longer duration storage, which is what the market signals are telling us is needed in years to come, those costs just go up. You take advantage of some economies of scale through purchasing power, but the actual technology doesn't change as you buy more and more hours of storage. So that's where our system comes in. I've added 3 blue lines here. The top blue line is the costs based on our first-of-a-kind prototype that we're building right now as part of the LODES project. The line below that, with the slightly fatter dotted lines, is our projected costs for a first-of-a-kind commercial plant. That's assuming about a 30% cost reduction, which we feel is entirely reasonable. And the solid line at the bottom is an nth-of-a-kind commercial plant using a very reasonable 10% learning rate over the years. So the takeaway points from this are these 2 inflection points. The little star on the right shows that we expect to be cost competitive with lithium-ion for 24-hour installations within the next year or 2. And with cost reduction, that crossover point will drop down to 7 hours. And another way to say that is to look at this delta here. For a 24-hour installation, a system like ours would be half the price of a lithium-ion system. So that's the technology and a little bit about the benefits that we offer. So some detail about the LODES project. Like Danielle explained, it was a phased program. We kicked off in 2022 with the feasibility study. We had a reasonably low TRL, comfortably at 4, because we demonstrated some of the subsystems, but at scale. And over the following number of years, we've gone through a very traditional engineering process of completing the concept design, detailed design, and then launching into procurement, assembly, commissioning, and we hope to have a system operating at TRL 6 in 2025. We're working at quite large scale, similar, I think, in physical scale to some of Mike's equipment. You can see a sunny day in Scotland in the middle here. That's our support frame and some ISO tankers. That's just at the back of our building here, where we're starting to assemble the full system. And we're quite far ahead on some of the subsystems. You see an engineer here commissioning our electronics, and 2 of our test engineers running some compressor test rigs. So what does it all look like? Here's an illustration of what the full system will look like. So we've got a lot of equipment spread out. It's very much an experiment at this scale, and I very much chime with what Mike said about having easy access to equipment. It's not just so you can get in there and have a look and see what's going on, but also having space to build it in the first place. There's huge scope for cost optimization and condensing the arrangement for a more commercial project. So our objectives for 2025 are on the left. We want to show full charge and discharge cycles. We want to get hundreds of hours of operation and demonstrate the round-trip efficiency. And I think there's a question in the chat about this already. We're targeting a round-trip efficiency of 60%, which of course is lower than lithium-ion batteries and pumped hydro might offer. But based on market trends, we see such volatility in power prices that perhaps round-trip efficiency isn't quite as important as you might think it would be. And CapEx and ancillary services probably have a bigger part to play in the revenue streams for an energy storage operator. And the final point that we really want to do is to validate our digital twin. We've modeled all the equipment to a very high degree of detail, and we're using that to forecast performance. Once we run the experiments, we'll be able to validate a lot of the assumptions in the model and decide where to focus engineering efforts on iterating the system for what comes next. And speaking of what comes next, we can reflect also on some learning from the project. I think the phase project approach that DESNZ deployed of having a feasibility stage first is absolutely the right thing. That lets the team consolidate a design. It might not be the design, but it's something to base a bid around and structure a delivery team around. The DESNZ team have been extremely supportive, and I think that stems right from the political level right down to the execution level. They've got DESNZ have some good systems and project controls in place, but have all the way through been very supportive of an R&D program, which is what this is, and with that come changes, and they've understood that. The one negative, I think, to reflect on is perhaps that the timeline for phase 2 was a little bit short. 23 months is not a long time to complete detailed design and deliver a project of this scale. So perhaps for any future projects, that's something that public partners might want to think about. In terms of project delivery, R&D can be difficult, but the way to mitigate that is to work with a trusted team and partners. We've got a team of 25 people, and I think about 20 of those have all joined the team through word of mouth or the wider network. And our partners, 4 out of our 5 key suppliers or partners were actually well known to us from before the project. Some are ex-colleagues from previous walks of life, and all motivated similarly and trusted to execute the packages of work that were entrusted to them. That's the positives. I think the negatives we need to respect is that manufacturing capacity in the UK at the moment is very constrained, and I don't mean that that's just because there's a lot of demand. It's just because the supply simply isn't there. A lot of manufacturing historically has been offshored. We've found that some specific equipment has had to come from literally all over the world. We've had parts come from China, Italy, Central Europe. And with that comes logistical challenges. I show the little railway map there from China to Central Europe, because we had one part coming from China, which was going to come on a ship, but then there was some geopolitics in the Red Sea that meant that part then had to go on a train through Russia, just as the war in Ukraine was kicking off. So that led to some interesting discussions with our freight forwarder. And again, on a short project, you can't really afford to have long delays. So these things need to be well balanced. But then to take away the huge positives that we've found on this project, clearly there's the engineering development, but there's also the market focus. I think the long duration energy storage opportunity is actually much bigger than we'd expected. The level of engagement we've had with other market stakeholders has been tremendous, and the hockey stick deployment that we've seen in wind and solar is definitely continuing, and with that is going to come huge demand for energy storage, both short, medium, and long duration. The flip side to that is that a lot of projects are run by large incumbents. They tend to move slowly, so you need to pick who you target for, particularly for first-of-a-kind projects. But what's really helping that along is that policy is evolving very positively, particularly in the UK. I think the UK is a poster child in some respects. We've got DESNZ with projects like this, and now other stakeholders like Ofgem, very well positioned to move ahead with new policy implementations, and a very supportive government. So we hope to see similar signals from elsewhere around the world. And that's it from me and the team. Happy to take questions and continue the discussion. Thank you very much.
Okay, thank you very much, Jacob, and also to Mike before. So now we will move on to some questions. So already pointed out that there's a couple in the chat. So we'll go to Eric's question, which I know Jacob already answered towards the end there. So I'll just direct this at Mike. What is the round trip efficiency of your compressed air heat storage system?
Yeah, great question. So we're targeting 60 to 65% for our production systems. Prototype is a bit below that, but that's what we would have expected. And we've got a program in place to deliver that production efficiency.
Great. And then sticking with you, what is your cost per kilowatt and per kilowatt hour? Also from Eric.
Yeah, so we're looking at we tend to give costs in the kilowatt hour range, because that tends to be more useful for our kind of durations, 5, 10, 15 hours. So we typically look at something like 250 to 300 pounds per kilowatt hour for production systems.
Great. Okay. I will ask a question that I have for Jacob now, before coming back to the Q&A. So in one of your diagrams, Jacob, you showed that you store energy from the grid in both heat and cold systems. And I was wondering, in the case of the cold store, which you mentioned was very, very cold, minus 140, I think you said. I was wondering if this has applications outside of just the storage. So could it be used in refrigeration, for example, such as in the case of vaccines, which often have to be kept very, very cold? So I wondered if there was applications there, or do you envisage that in the future?
Thank you, Craig. And absolutely, yes. In fact, we've had a lot of interest from stakeholders who are interested in decarbonizing processes in industry, who have heat and cold as energy vectors around factories, particularly in pulp and paper and food and beverage. Food is an interesting one because they need heat often for cooking, and then sometimes also very cold temperatures for freezing a product before it's shipped off and warehoused and sent to supermarkets. They currently have systems that rely on resistive heating for the heating phases, and some kind of heat pump for refrigeration. And they have to buy power from the grid. So they're interested in not only having a way of controlling when they purchase electricity from the grid, thus requiring some energy storage, but also if they could have an integrated plant that does that and provides the heat and the cold for their internal processes, then that solves a lot of headaches and provides a much more cost-effective system. So yes, it's something that we're looking at, and it's been very much an output of this project, is that energy storage is the prime objective, but how users use that energy after it's being stored can be simplified by shortcutting the way the heat and the cold is generated.
Yeah, great, thanks. I think this next question is probably best aimed at Daniel, but both Michael and Jacob can chime in as well. So this is from Tim. He says, I thought that LODES was aimed at those days where there was very little renewables and only used a few times a year, but it seems like these options will shift power within a day. So what definitions of LODES, what definition of long duration energy storage did the UK government DESNZ use?
So for this particular program, we used charging and discharging for 4 hours, storing for 4 hours as well. Generally, there's been a lot of different opinions on what would count as long duration, etc. And based on where we thought the technology was and where we had the best chance of making progress, etc. We thought for this program 4 hours would be that spot, but we at the same time have thinking going on in terms of longer duration of storage, for example, seasonal storage, etc. Although the technologies in those areas are at a much earlier stage.
Great, thanks. Okay, so everyone keep your questions coming, but in the meantime, I have a question for both Mike and Jacob. So we'll come to Mike first with this. So in both of your presentations, you showed that your current sites are pretty large, and of course, they're aimed at commercial uses a lot of the time. But I'm wondering, do you envisage at some point down the line that you see these being feasible to be used for one house or maybe a small block of houses. So, you know, can someone come home from work at the end of the day and have a fully charged, you know, storage system that was hopefully charged by renewables, you know, solar and wind throughout the day, where it's much cheaper. And then when they get home, they have their fully charged storage system using your technology, and they can charge their electric vehicle and power their house during the day. So do you envisage being able to get it to that much smaller scale at some point in the future?
In very brief, no. I think the only cheesecake system inside someone's house is likely to be the edible kind. So I think the domestic application, I don't think the technology scales all the way down to one household. Having said that, that's not to say that it's not relevant at community level. So in terms of the housing estate, in terms of kind of community energy, and being able to kind of provide a neighborhood with power, absolutely. And I think that's a really interesting and positive way to be thinking about storage, that it is something that can be community level, and actually would be more cost effective for doing that, rather than one household having a battery, the next household not having a battery, and potentially driving some kind of equality challenges and inequality challenges, where we can bring people together to kind of to benefit from storage. I think that's really encouraging, and allow some exciting models from the community energy space to kick in. So there is a natural floor on how small our systems will go. We won't be going down to lawnmower engines for individual houses. We're going to stick with truck engines and bigger, but that doesn't mean that Cheesecake can't be a part of kind of unlocking clean power for people's homes.
Yep, and pretty much the same answer from me, Craig. Our system does have a natural floor, sort of the single-digit megawatts, and I think we wouldn't go to less than 5 hours of storage. So 5 megawatt hours would be pretty much the smallest system. But we do see opportunities very much at the distribution level rather than necessarily transmission level, and enabling new housing developments in places where the grid is constrained is very much an area that we've looked at. So yeah, absolutely.
Great, thanks. I'm not seeing any more questions coming up. So if that's going to be the case, then I think we can pull it to a close there. I think you both had your contact details on your final slides, was that right? So if anyone has any other questions, those people watching the recording, for example, they can reach out. And then as I mentioned in my intro, the next webinar won't be until February, featuring Icebreaker 1, so we'll see you then. But I think that's it, so we'll call it to a close. We'll thank our speakers again, and thank everyone for coming.